Okay, welcome to the Wellness Channel. Today we have the pleasure of having our colleague, esteemed colleague, Carlo Fiscione from the Royal Institute of Technology in Sweden, KTH, with us. And Ryan is going to give a talk about our latest work together with Carlo on computing. Well, we would like to bring it to eventually to over-the-air computing. At this point, it is more integrated communication and computing using dirty paper strategy. So, Ryan, please go ahead.
So, hey everybody. Yeah, as Professor Abru mentioned already, this is a joint work with KTH that we started. So this team is going to be computing on dirty paper, interference-free integrated communication and computing. So as a rough overview, is going to be a way to combine the functionalities of communications and computing using a dirty paper coding framework that was first introduced by Costa in the 90s. So yeah, let's jump straight into it. So let's start with the typical system model that we use for computing, for example, where you have a SIMO uplink case with multiple single antenna UEs, users, and also a base station, a receiving base station with multiple antennas. So in this case, we consider that we have K users and N antennas. And each of these users wants to transmit some symbols, so communicate over some data symbol, and also and the base station also wants to compute some symbols, compute a nomographic function, for example, at the base station. So this is actually arbitrary because it depends on what type of computing we are doing to define the function that we use. But for all intents and purposes, we can just consider, for example, an example scenario where the base station wants to estimate all the data symbols, so the data symbol vector D. So we would have K symbols and also a single function, which is going to be defined as the arithmetic sum of the computing symbols Sk. So this is going to be the typical system model that we use when we are talking about this. And here's the fundamental framework that we can use. So for example, if you transmit xk, which in the state of the art is usually a concatenation of both the computing and communication the signals, you would have your xk to be dk plus sk. So this can also be thought of as some sort of superposition coding, but for generality and also to be rigorous here, it's just like a simple way of combining these two functionalities. And also you have your received signal then at the base station, which is going to be given by your equation 1. So y is a vector of m by 1 at the n antennas, and hk is your channel vectors for each user, and your xk is going to be the concatenated transmit signal plus, of course, the AWGN noise at the receiving base station. So the goal, as I said before as well, is to estimate all your symbols, all your k data symbols, dk, and also compute the sum of SKs at the base station. So now, so far in the state of the art, there has never been a way actually to use the knowledge that each of the transmitting users knows its own dk and sk. So this has actually not been leveraged before, and this immediately points to the way that Costa initially envisioned his dirty paper strategy, because the dirty paper coding strategy, let me just go here, is actually a fundamental idea where one says that if you know your own interference at the transmitter, you can transmit in a way such that the receiver cannot see the interference. So it's a way of coding that actually lets you know this. And these 2 points are highlighted here that, for example, mathematically given a received signal y equals x plus s plus w, where x is what you want to decode, s is your interference, your known interference, and w is your random noise. You can perfectly recover x at the receiver, even when your s, your interference, is unknown at the receiver. And how would you do this? The fundamental assumption is that your S, your interference, is known at the transmitter, and you can use these dirty paper coding principles to remove the interference completely. So in our case, it's a bit, we are not saying that our S is interference. Our S is a computing signal, And we actually also want to estimate S. So this is the fundamental difference between what the initial fundamental idea was and what we are going to propose now. So one way to do this dirty paper coding operation is via nested lattice codes. So some alternative methods are also, for example, the basic method would be Tomlinson-Harashima precoding. But for the sake, since we also want to somehow embed the removal and recovery of interference as well, we decided to take a first approach using these nested lattice codes. For more information on these codes, you can look at the paper that's referenced here by Ares. So we are going to use the jumping straight into the nested lattice code structure. We are going to use the Gaussian integer lattice, which is defined in this way. So it's just a plane of complex numbers, and these complex numbers, each of the components are integers, right? And we can also now define a coarse lattice on this Gaussian integer lattice, such that we have a spacing delta. And we do this so that we limit our transmit power when we code this. So as a visualization, here you go. This is going to be the standard Gaussian integer lattice. And for the people who are more from the coding background, the standard Gaussian integer lattice is actually a code where your generator matrix is identity. So in that sense, that's why it's called the standard Gaussian integer lattice. So this is going to be what the points look like on the lattice, where when your delta, your bounding region is 2, and your rate is 1. So as in the number of bits per axis. So more on that later. And when you now define the coarse lattice, you see when you choose your delta to be 2, you're going to sample your grid, your lattice at every second point, and you're going to have these red points, which are going to be a coarse lattice structure. So now we can also define a fine lattice as lambda f, as you can see here, where your small delta is going to be dependent on the number of constellation points you want inside your region, and of course your number of bits per complex symbol. And of course, since this is the nested lattice codes, you also need a notion of a coset, where each of your transmit symbols have to correspond to a coset that's shifted according to the coarse lattice. This is also going to be visualized, but one important point to note is that the transmit constellation is actually the set of all coset representatives inside one Voronoi region and not the entire coset. So that's an important distinction to make. And these are all coming from the fundamentals on lattice coding. So these are going to be the fine points inside the lattice. So as you see, these blue points, as before, were the standard Gaussian integer lattice, and these red points were the coarse lattice. And now when you sample this into a final lattice, you get these gray points inside each of the coarse lattice cells. For example, I think this is also better visualized once we have definitions for our fundamental Voronoi region. So let me just show that here. So you see here, this is going to be a Voronoi region, this area surrounding a coarse lattice cell. And inside this region, you're going to have your symbols. So these symbols are actually what you want to transmit, and you can code them in such a way that recovery approaches the capacity of the true Gaussian channel. So going on to the transmission strategy, we now assume that each user knows its own data symbol and computing symbol such that it can do this operation as given in equation 4. So you see this VK is now going to be a modified transmit data symbol, and it's calculated by picking out points from the constellation corresponding to the, for example, QAM alphabet, and then taking the difference between that and the computing symbols, of course, based on the lattice that we defined. And an interesting opportunity also presents itself here in the sense that we are going to also choose our computing symbols in such a way to try and minimize the orthogonality. Of course, a naive way to do this would be to rotate them by 45 degrees, which is exactly what we do here as shown. So this is the figure that we had before, but now we explicitly define our transmit data symbols as these green points over here. So yeah, these are the fine points inside our original lattice. And we choose our computing symbols to be 45 degree shift of these symbols. So these black points that you see here are going to be your computing symbols. So I should also probably make the point here that this is in no way we are not claiming this in any way to be optimal. There's probably much better ways to do this as well. But for an initial work, this is potentially one of the ways to try and minimize the distance between the Euclidean distance between these points, the communication and computing points. So now we can express our multifunctional transmit signal. So that is to say our communication and computing signal by equation 6, where now your VK is no longer the naive communication symbols. It's carefully picked and coded symbols from the lattice structure. And you can go ahead now and transmit your X's over a Gaussian channel. For example, in this case, we chose a Rayleigh fading channel. And you're going to have equation 7 here. And also we take into account the fact that we are going to have multiple frame transmissions over this channel, because as you can see in the latter part, it's going to be useful in the computing estimation part. So where we have now this matrix relationship where this Y contains multiple frames of your received signal, and of course your X is also your composed of now your V tilde and your S. So it's probably also noteworthy that each of the data transmissions at each time slot are completely distinct. So you're going to be transmitting different data at different time slots. So you're going to have no loss of rate in that sense. But for the computing symbols, we are going to transmit the same computing symbols over T time slots. So for example, T can be either 5, for example, or 10. Yeah, and the computing symbols are going to be the same. So for the decoding of the communication symbols, you can use a typical lattice coding strategy that we have, and first obtain an MMSE estimate using equation 8. Of course, we assume for first work that we have perfect CSI at the receiver, and we can now define a temporary variable such that we apply this modulo operation to this decode LMSE estimated transmit signal. And then we do another operation to map the points that we decoded onto the fine lattice, so which is defined as in equation 11. So this Q of lambda f is going to be the fine lattice nearest neighbor quantizer that we use. And once we have done this, we have perfectly estimated now the data symbols. So, and now all that's left to do is use these data symbols that we have done and try to recover a computing symbol estimate as well, which is as a first point done in equation 12. So here we build the maximum likelihood estimator for our computing symbols. And I also would like to make the distinction here that this is strictly speaking not over there computing, because we are still estimating each of the symbols separately. But it's also very useful because this somehow proves to be a bound of sorts, just to as a proof of concept fact, just to prove that we can extract this known interference kind of thing at the receiver as well, which has never been done before in the dirty paper literature, because it's always been the assumption that this known interference is unnecessary. So there was no reason for us to want to also estimate this known interference at the receiver, but now we do. So this is a baseline scheme just to show that a proof of concept to show that this type of scheme could technically work. And of course, we are going to explore further details to make this into a fully over-the-air computing strategy by estimating the functions themselves instead of this. But yes, this for now, the estimator is done across T time slots. And finally, after you recover your S's, you can compute a target function according to 13. And of course, a note on the complexity as well is, of course, since this is a maximum likelihood estimator, it's a hard search. So it's an NP hard problem, and of course the complexity will scale according to your constellation and your number of users, right? And it will scale exponentially with the number of users, since you have to build the different combinations for each constellation symbol. Yes, so these are some of the results that we have for this initial work. So as you see here, the state-of-the-art methods given in reference 8 actually fail completely, in the sense when we have equal powers for both the computing and communication. And this dirty paper proposed strategy actually comes really close to the QPSK limit, as to say, if you had only data and you only wanted to do communication over a really faded channel, for example, this dashed line is the performance that you would have, and this red line is what we are proposing. So it's very close, as you can see. And of course, this solid black line is the bit error rate if you have the full power to dedicate to your communications. And what's interesting here is that throughout the T frames, we now also have a very good computing performance. So as you can see, the mean squared error decreases, and of course flattens out a bit. And of course, if you want to mitigate that issue, you just have to increase the number of frames in the computing part. As you can see, the communication performance is almost the same. There is no difference here, but once you increase the number of frames, so this is for a case with 10 frames, as opposed to the 5 frames that we used before, the mean squared error just decreases with the proper linearity, as we can expect from a computing operation. So this is it for this short presentation. Do you have any questions?